Hi guys, today we're going to be focusing on polar and non-polar molecules. I'm excited about this video, so let's get straight into it. You'll be delighted to know that there's only one key term that we're going to focus on today, and that's a polar molecule. A polar molecule is a covalent molecule that contains one or more polar bonds and an overall dipole moment. So let's jump into what that means. Now, polarity of molecules. When you have polar bonds in a covalent compound, that may result in the entire molecule being polar. So having ends of slightly opposite charge. Polar molecules are therefore said to have an overall dipole. Now this is the example that we looked at in the last video to do with polar bonds. So HCl, we have a polar covalent bond, so an uneven sharing of electrons. Polar bears are greedy. Chlorine has the greater electronegativity, so the shared electrons are going to be shifted slightly towards the chlorine, giving a slight negative charge. So that's the delta minus and the delta plus on the hydrogen. So that's a polar bond, okay? Now we're talking about polar molecules. Now HCl is a polar molecule because there's an overall dipole. So remembering a dipole is when you have either end of a bond or a molecule that has a partial positive and a partial negative charge, so a difference in charge. So in this case we have HCl, and the overall molecule has a negative end and a positive end. So that's considered a polar molecule. At this point, I'd like you to pause the video just for a second and record this in your notes. So the conditions that must apply for a molecule to be polar. First of all, it must have polar bonds. So if there's no polar bonds within the polar molecule, it's going to be a non-polar molecule all the time. The second criteria is the partial charges created by the different electronegativities must be distributed asymmetrically across the molecule. Asymmetrical. So what does that mean? I've got a bit of a diagram here to try and explain symmetry. So we have a symmetrical clown face here, nice happy little clown. And you can see the dotted line of symmetry going down the middle of the face there. If you look on opposite ends of the dotted line, you've got the same half of the face. It's just kind of flipped in the opposite direction. Okay, so it's nice orange smile curving upwards on the right side, and it curves upwards on the left side in exactly the same way. So that's symmetry. Asymmetry is the opposite. So we don't have the same thing on opposite sides of the line of symmetry. So it's a pretty silly example, but you've got the eyebrows are completely different. The eyes are a different shape. The eyelashes are going up. That are curled a bit funny. And I don't even know what this is. The nose is different. The mouth is different. So this is quite a scary, asymmetric looking clown here. So the steps to determine the polarity of an unfamiliar covalent molecule. So we're going to have some practice doing this. Step one, you want to draw the structural formula of the molecule. Now that's something we've covered previously in class, and if that's something that you're having difficulty with, it might be best to talk with me about it. Use VESPR to determine molecular shape. Now hopefully you remember what VESPR stands for. It's the valence shell electron pair repulsion theory. An exciting theory that says that bonding and non-bonding electrons are spread, distributed evenly around the atom. Use electronegativity values or the position on the periodic table to determine bond polarities. So that's what we covered in the previous video. Use the shape and bond dipoles to determine whether the molecule is polar or not. So you're using molecular shape and the dipoles, or the opposite partial charges in the bond, to determine whether the molecule is polar. Now that probably won't make too much sense until we have an example, so let's do it. Oh, sorry, I've got one more thing here. Just remember that symmetrical molecules cause bond dipoles to cancel each other out. Okay, so if you've got symmetry, then bond dipoles are going to cancel. Just like in maths, you might have a positive and negative, and they'll cancel out. Before we begin determining our polarity of our molecules, we need to be able to draw the molecules. So I've got 3 here, and I would like you to try and pause the video in a moment and draw the valence structure of these molecules in either your notes page or your exercise book. Okay, so pause the video now and see if you can draw these molecules. Good luck. Okay, so here's the first of our 3 examples where we're going to determine whether the molecule is polar or non-polar. We started off with carbon dioxide. This is the valence structure for carbon dioxide. We've got double bonds between the carbon and the oxygen. Carbon has a covalency of 4. Carbon always forms 4 chemical bonds. Oxygen has a covalency of 2. So oxygen's going to form 2 covalent bonds. So by having double bonds between each carbon and oxygen, all of those atoms fulfill the octet rule. Oxygen has 2 lone pairs of electrons coming out the side. So do we have polar bonds now that we've drawn the structure? Well, we've got delta minus and delta plus. Oxygen is more electronegative than carbon based on its position in the periodic table. So we do have polar bonds here. Oxygen is greedier. It will hog those shared electrons and it will have a slight negative charge, delta minus and the delta plus on the carbon. And the same thing over here. So polar bonds, we'll give that a big tick. Okay? Is the molecule asymmetrical? Okay, so is there no symmetry here? Now what I mean is there an end of the molecule that's different, or are the ends of the molecules the same? So on the left hand side of the molecule we have a negative charge. Okay, so all of this part here is negative. Let's look on the right hand side of the molecule. All of that is negative as well. So you've got the left hand side and the right hand side that are negative. So that molecule is symmetrical. Okay, so those dipoles are going to cancel each other out. Okay, so asymmetry is a big cross. It is actually symmetrical. So is it a polar molecule? No, it's not. How surprising. Even though you've got polar bonds, it's actually not a polar molecule because that symmetry on the left and right hand side cancels out the overall dipole. So the overall dipole of the molecule is cancelled out, so there's no difference in charge on either end, and it is not a polar molecule. Here's our next example. So this is formaldehyde, CH2O. So hopefully we figured out how to draw it. Carbon's the central atom because it has the highest covalency of 4, 2 bonds to the oxygen and single bonds to the hydrogen. First of all, to determine whether it's a polar molecule, do we have polar bonds? Yes, we do. We've got a delta minus on the oxygen, and we have a delta plus on the hydrogen. So there's a polar bond between the carbon and the oxygen, and a polar bond between the carbon and the hydrogen. It's actually considered non-polar here, but we'll discuss that in a later lesson. So we're just going to say polar bonds yes for now. Okay. we've got differences in electronegativity between the carbon and the oxygen, mainly. Do we have asymmetry? Now let's have a look at the molecule here. On the left-hand side, we have a partially positive end. So we've got that positive end on the left. On the right-hand side of the molecule, we've got a partial negative, a delta minus. Okay, so we do have an overall dipole here. On the left, positive. On the right, negative. So asymmetry, I'm going to give it a big tick. Is it a polar molecule? Yes, it is. Polar bonds, it's not symmetrical, so it's a polar molecule. You've got an overall dipole here. Last example, we have tetrafluoromethane, CH4. So we have the carbon central, and we've got 4 fluorines coming off. Now remember, this is the 3D structure, so the bonds aren't kind of separated in a cross like they would be in a 2D structure. Now, do we have polar bonds? We've got a delta plus on the carbon and a delta minus on the fluorine, because fluorine is more electronegative than carbon. So we do have polar bonds. Is there asymmetry? The left-hand side of the molecule over here, negative. The right-hand side, negative. The bottom, negative. The top, negative. So all around the molecule is negative. So those dipoles cancel each other out. Okay? The left cancels out the right, the top cancels out the bottom. So asymmetry, no. There's lots of symmetry in this molecule. There's symmetry going this way, and there's symmetry going this way. Is it a polar molecule? No, it's not. It has polar bonds, but because it's symmetrical, the overall dipoles will cancel each other out. So there are a few examples. Hopefully that's given you a taste of polar or non-polar molecules, and I look forward to practicing it more with you in class. Signing off. See you later.